Okay, so we're going to start looking at inverses of functions. So at the end of this lesson, we'll be able to identify the inverse of a function by looking at its graph. And we'll also be able to determine the equation of the inverse if we're given an algebraic expression of a function as well. So what we're going to start with is we're just going to take a look at this function f of x, and we're going to graph it. And just like you would with any function that you don't know how it behaves, what we should do here is we should make a table to graph this function. So over here on the side, you're probably going to have your inputs, and you're going to have your outputs, and we're just going to graph what this function would look like. I would encourage you to pause the video and graph it yourself, and then check your work with us here. All right, so an easy number to plug in is 0, and if I plug in 0 to this function, I end up with an output of 1. I could plug in a 1 to this function. It looks like I would get 3, and all I'm doing is plugging these values in here and here. So when I plug in a 2, I'm going to get 2 squared, which is 4, plus 2 is 6, plus 1 is 7. Okay, so an input of 2 gives us an output of 7, and we're starting to see this function take shape. If I plug in a 3, I'm going to get a number that's not within the range of what I see here. So 3 squared is 9 plus 3, and I'm already off the graph, right? So I'm not going to plug in a 3. I'm going to go the other direction. Negative 1 squared would be 1, plus negative 1 would be 0, plus 1. All right, so that gives me a 1. All right, and a negative 2. If I plug in a negative 2, I'm going to get 4 plus negative 2, which is 2 plus 1 is 3. And you're starting to see some symmetry here. It'd be great if I had left myself some space, but it looks like I could do a negative 3. I'll just make another separate table here. If I plugged in a negative 3, it looks like my output would be 7, and I can check that real quickly. 3 times 3 would be 9, plus negative 3 would be 6, plus 1 would be 7. Good. So I'm going to plot these points. So these are the points that we figured out are on this parabola. I'll tell you that the point negative 0.5 is also on this parabola. And we know that it exists everywhere because it's a polynomial, and we know that their domains are not restricted. So this is kind of what that function looks like. All right, so we've graphed it. The next thing we're going to do is we're going to plot something called the inverse of this function. So what we need to do here is we need to define what the inverse of a function is. Okay, so this is a definition that you're going to want to have. The inverse of a function is a reflection of the original function over the line y equals x. So while you are writing that definition, I'm just going to sketch that line y equals x here so that we've got it on our graph. This is what that line looks like. So this is the line y equals x. It's got a slope of 1, a y-intercept of 0, right? So we know that that's what this line looks like. So if I were to take this function and reflect it over this line, what would that look like? Well, it would kind of be like if I were to turn my graph and look at this as the line of symmetry, all my points, just draw in green here, all my points would just flip right over that line of symmetry, and even the ones from back here would do the same thing. Each point is going to reflect over that line and end up somewhere else. So the question just is, where will it end up? Well, let's pick an easy point here to start with. I'm going to plot this inverse function in black. So let's pick this point here, the point 0, 1. If I reflect that point over this line, and I go down 1 to the line and over 1 away from the line, I end up right here at this point. That point is a reflection of the point 0, 1. So I'm going to write that point in 0, 1. And you notice that its reflected point over this line is the point 1, 0. That's not a coincidence. For example, this point here is the point 1, 3. When I reflect it, I will end up at the point 3, 1. And you can see this pattern start to emerge. If this is the point 2, 7, then its reflected point is the point 7, 2. And we start to map the path of this parabola. And all of these points get reflected, and I end up mapping the path of this parabola. So my point that was negative 0.5, positive 0.5, is now the point positive 0.5, negative 0.5, and I can keep plotting the rest of these points, and I end up with what looks like a parabola on its side. So that's what your reflected function looks like. That is the inverse of f of x. So an important note that we're going to want to make here now is, as we're talking about the inverse of a function, inverse points are just taking those coordinates and flipping them. So let's record that here. So as an example here that we maybe want to hang on to, if f of x, if we have some function that contains this point, the point 3, negative 1, then f inverse of x, that's what this little notation means. It doesn't mean f to the negative 1 power. What it just means is the inverse function of f contains the point negative 1, 3, because it's been reflected over this line, and so we just flip our x and y coordinate. All right? So anytime you see two functions that look like mirror images of each other over this line, they are inverses of each other. So it's important to kind of establish that definition before we get into doing this algebraically. So now we've got a function called g of x, and we need to determine its inverse, but we don't even know what it looks like. So what we're going to do is we're just going to remember that anytime we use the inverse, the y coordinates become the x coordinates, and the x coordinates become the y coordinates. Okay? So to start off, let's call g of x y for now, because we've been using the terminology y equals here, flipping y coordinates and x coordinates. All right? So starting with that, since we know that the new function we're going to be dealing with is going to take our x coordinates and make them y coordinates, and make our y coordinates and turn them into x coordinates, we're going to do exactly that here in the equation. Right now I'm going to flip my x and my y. So we should maybe make some steps for ourselves. If we're going to find the inverse algebraically, we just have two steps. Step one, we need to flip x and y. We need to flip those two variables. And now if I want this equation, I need to get y alone, because our equations usually say y equals, right? So I'm going to get y alone now. I'm going to start by subtracting 4. All right, now I have x minus 4 equals 3y plus 1 over 2. I'm going to continue this over here. To get rid of this denominator of 2, I'm going to multiply both sides by 2. So times 2 times 2. So now I have 2x minus 8 equals 3y plus 1. Now again, I can subtract that constant on the end, and I'll have 2x minus 9 equals 3y. And finally, I'm going to get rid of that 3 by dividing by 3. Divide everything over here by 3. So I end up with 2x minus 9 over 3 equals y. So what did we just do there? Well, that was step 2. Step 2 was solve for y. And now we have that equation. The one thing that we got to be careful of here is the original function was called g of x. And remember, we've got this inverse notation, so we have to make sure that in the end we remember to not call it y, but to call it g inverse of x. 2x minus 9 over 3. And that is your inverse function. So what that means is, if I were to graph this function g of x, and then graph this function g inverse of x, they would look like mirror images of each other reflected over this line, y equals x. And they would if I graphed them, and you could test me if you'd like to. So before you come into class tomorrow, what I'd like you to do is do the same thing with h of x. Right here, this function h of x is given, and I want you to do the work and determine the equation of h inverse of x, and then we'll practice when we get to class.